Hello and welcome to another lecture of CSE331 Automata and Computability. My name is Ajwadanjum Islam and today we will continue on with the second part of our concept and terminology lecture. We are already familiar with the concepts of languages and alphabets. If you recall, languages are just set of strings. In this first example, we have all the possible integers from negative infinity to positive infinity. One thing you have to remember that every member of this set are strings. So this 0 or this 1 might look like they are a number or a single digit or a single character, but you have to treat them as strings. In the second example, we have all possible strings that you can construct using the symbols x and y. A language can even have only one string in it, and this string can even be the empty string. A language might have nothing in it, so this is an empty language. Please focus on the last two examples here. These two languages might feel similar to you, but they are not the same language because this language has a member. The member just happens to be the empty string. In this language, the language itself is empty, so their cardinality will be different. Every language has an alphabet of their own. This alphabet defines what are the symbols that we might encounter in the strings of that language. If you don't remember what alphabets are just a set of symbols. Let's take a familiar example. In the Bangla language, there are an infinite number of strings, but in all of those strings, we are only going to encounter a finite number of symbols, the Shorobarnos, the Banjan Barnos, and all the punctuation marks. So if I'm reading a Bangla text, for example a Bangla book, I'm not going to encounter some random Chinese characters or some Egyptian hieroglyphics. Similarly, if we have a set that contains all the binary strings, we know binary strings are made of only two symbols, 0 and 1. So in all of these strings, we are not going to encounter anything like a Boishono law or the number 6. If we have a set or a language that contains all the valid phone numbers of Bangladesh, we are only going to encounter digits or the hyphen or the plus sign in all of those strings because phone numbers don't contain a $sign or English letters. Alright, so let's talk about the relationship between a finite state machine and a language. So this is a generic finite state machine. It has some inputs in it and some of those inputs are going to be accepted and some of those inputs are going to be rejected. For this example, let's assume that our machine can detect all those positive integers that has a length of 2. Now we already know that inputs are going to be strings, something like this. But not all strings in the universe is acceptable for all the machines. This machine only deals with integers, the positive integers. So in the alphabet of this machine, we are only going to have the digits from 0 to 9 and the plus and minus sign, and all the strings must be constructed using those symbols. So something like this is not an acceptable input for this machine. Of all the strings that are actually acceptable, some of those inputs are going to be accepted, like 0, 197 are not integers that has a length of 2, and minus 15 is not even a positive integer. So if this machine is even half as good as it claims to be, these 3 strings are not going to be accepted. But you have to remember that this machine obviously doesn't only accept these 4 strings. There are numerous other strings that will be accepted by this machine, and of course numerous other strings that will end up being rejected. Now please focus on this set. The complete set of strings that are accepted by a machine is called the language of that finite state machine. If the finite state machine has a name, for example if we call this machine A, the language is generally called L of A. Now here is a quiz for you. For this particular machine, the language of this machine, which means the set right here, the complete set, do you think that set is an infinite set or a finite set? The question is not very hard, so I hope if you think about it, you are going to come up with the answer on your own. We know languages are sets, so all set operations are going to be applicable on languages as well. Here are some set operations that we are all familiar with. We have the universal set that contains all the members, all the elements of the universe. And if we have a set A and set B, their intersection will only contain the elements that are both members of A and B, and their union is going to contain all the elements that are a member of either A or B. The complement of a set contains all the elements that are not a member of the original set. So in this example, we have everything colored except for A. So let's say we have an alphabet that contains the two symbols A and B. What do you think will be the universal set or language for this alphabet? A side note here, alphabets are generally described with the Greek capital letter sigma. Anyway, back to topic. Universal sets are going to be the set that contains all possible strings that you can construct using the symbols of the alphabet. So in this case, any string that we can construct using A and B is going to be in the universal set. Please note that the empty string epsilon is a member of all universal sets. Moving on to the union of two languages. If a language L1 has some strings and another language L2 has some other strings, their union is going to have all the strings from L1 and all the strings from L2. In this example, L1 is an infinite set of A, AA, AAA, and so on, and L2 is a finite set that contains only 3 strings. So obviously, their union will have these 3 strings and all the other strings from L1 as well. If the alphabet of L1 is A, and looking at these 3 strings, the alphabet of L2 will contain these 5 characters at least. What do you think will be the alphabet of the union set? The alphabet is going to be the union of these 2 alphabets. Let's look at another example. If A is the set of all odd binary strings and B is the set of all even binary strings, in their union we are going to have all possible binary strings because every binary string is either odd or even. Their alphabets are 0 and 1, 0 and 1 in both cases, so the union alphabet is going to be 0 and 1 as well. So let's look at the intersection of two languages. If a language has some strings and another language has some other strings, their intersection will have only those strings that are present in both languages. So let's look at the previous example one more time. In these two languages, only the string A is common in both, so their intersection will have only one string. What do you think will happen to the alphabet? The intersection language will only require the symbols that are present in both sets, right? So the alphabet is going to be an intersection of the other two alphabets. Let's look at the example one more time. We have the set of all odd binary strings and the set of all even binary strings. If we take the intersection, there will be nothing in common, so the intersection will be an empty string because no string that is odd is even and vice versa. Their alphabets are the same set, so the intersection will be the same set as well. There will be no change there. Moving on to complement. The complement of a language contains every strings that are not present in the original language. So if we have a language that contains these 3 strings and the alphabet is the symbol A, what do you think will be in the complement language of L? Well, looking at the alphabet, we can see that the universal set will contain all the strings that can be constructed using A. Of all these strings, the first 3 are already members of the language L, so the complement will have everything else but these 3 members. In another example, if L is the set of all binary strings that ends with 1, the complement language will have all binary strings that does not end with 1, in other words that ends with 0. Because all binary strings either have to end with 1 or end with 0. The alphabet of a language and its complement are going to be the same because the same symbols are constructing the strings in both cases. Moving on to the concatenation of two languages, this is important because this is slightly new. Concatenation means joining together, so we are going to join together the strings from the two languages. So if we have a language A and a language B, we are going to take a string from language A and take a string from language B and join them together. We have already seen how to join two strings or concatenate two strings in our last lecture. To find out the entire concatenation set of A and B, we'll have to take all possible combination of all the strings of these two sets. Concatenation is dependent on order, so if we were trying to create B.A instead of A.B, we'd have to take all the strings in the other order. Now let's look at the alphabets of the concatenation set. In this example, language A has an alphabet of A and B, language B has an alphabet of 0 and 1. What do you think will be the alphabet of the concatenation set AB? If your answer was the concatenation of the original 2 alphabets, then unfortunately that was not correct. We require all the symbols of language A and all the symbols of language B because we are taking strings from both sets, so the answer is actually going to be the union of the original 2 alphabets. We can concatenate a language with itself. In this example, let D be a set where it contains all the digits from 0 to 9. All these members are also strings, so the set D is also a language. Now if we concatenate D with itself, what do we get? If you take a moment and try to do it yourself, you will see that the set contains all the numbers from 00 to 99. This set is also referred to as D square. Similarly, if we concatenate D one more time, we'll get everything from 000 to 999, and this set is going to be referred as D cube. If we do it one more time, we'll get D to the power 4. So what do you think is going to be the set D to the power n? Now look at the first three examples. D2 is basically all 2-digit numbers. D3 and D4 are all 3-digit numbers and all 4-digit numbers. So D to the power n is just going to be the set of all n-digit numbers. So what do you think is going to be D to the power 0? If you had guessed the empty string, then you were correct. And now the interesting question. If we take the union of all these sets, what do you think we get? We will have every 2-digit numbers, 3-digit numbers, 4-digit numbers, and so on. So basically, we will have any numbers of any length. This is called the Lin closure. More on that on the next slide. The Lin closure is formally defined as such: the union of every single power of a set. There is a variation that is called the positive closure, that is also defined by the union of all the powers of a set, but the difference is the zeroth power is not present in the positive closure. So what does it actually mean? If a set contains the two members A and BC, their Lin closure will be this set and their positive closure will be this set. Note that the positive closure does not have the string epsilon, because that is the zeroth power of L. All the higher powers are present in both sets. So the only difference between the Lin closure and the positive closure is that the positive closure does not contain the empty string, unless the empty string is already a member of the original set. Now let's say we have an alphabet sigma that contains a number of symbols. What do you think will be the language that contains all possible strings that can be constructed using these symbols? Or in other words, what will be the universal set for this alphabet? Well, sigma to the power 1 will have all the symbols of length 1, that means the symbols themselves. Sigma to the power 2 will contain all the strings of length 2 that can be constructed using these symbols. Sigma to the power 3 will have all the strings of length 3. So simply, if we take the Lin closure, we will have all the strings of every possible length that can be constructed using the symbols. In other words, we will have our universal set. So this is important. If we take the Lin closure of the alphabet, we get the universal set. So to summarize, let's say we have a finite state machine called M, which has an alphabet called sigma. The possible inputs for M is going to be every member of the universal set, that is sigma star. The accepted strings will form the language called L of M, and the rejected strings will form the language that is the complement of L of M. Let's look at an example to solidify our concepts on all of this. Let's say we want the language that contains all valid Java identifiers. Now what are the valid Java identifiers? For a string to be considered as a valid Java identifiers, it has to maintain three conditions. The identifiers may contain only lower and uppercase letters, or digits, or the $sign or the underscore, nothing more. The identifiers must have a length of 1 or more. The identifiers must not start with a digit. So to solve this problem, let's first define a few sets. First of all, we have the set of letters. All the small and uppercase letters are in the set L. We have the set of digits, and we have the set of symbols that contains the dollar and underscore sign. Now, to get the alphabet of the Java identifiers, we need to take a union of all these three sets. If we take a union, we get a set that contains all the symbols we might encounter in a Java identifier. Now, to create any string of any length using these symbols, we need to take a closure. But the closure is not going to be the Lin closure, because the Lin closure contains the empty string epsilon, which has a length equal to 0. But our condition dictates us that the length of the string must be 1 or greater. So we need the positive closure. Now we have any string of any length using these symbols, but there is still a problem. The string cannot start with a digit. To solve this, we are going to concatenate something at the beginning of the string. This set does not contain the set of digits, so anything that comes from the set must be a letter or a symbol. Our problem is now solved, but there is still a minor tweaking that needs to be done. Now that we have ensured a symbol is coming from this set, we don't need a positive closure here anymore. We need the Lin closure, because now we can allow an epsilon to come from here so that the strings that are of length 1 can still be constructed. I hope that was not too confusing. If it was, however, I would encourage you to construct all these sets on your own using a pen and paper, and I'm sure you will get the hang of it. So that's it for today. Until next time, thank you.